Start recording and Freigabe. Das ist das Richtige. I think that's the right window. Good. So, as you might remember, the last time we have started our shellcode, and today we will try to finish it. So, writing shellcode is quite a laborious endeavor, but it gives you also a huge amount of flexibility. And so, as you might remember from the other injection mechanisms which we have used, like create remote thread or the user asynchronous procedure call injection, these were really reliant on the very particular behavior of load library W, which just takes as only one argument a pointer to a simple string, and that's it. As mentioned back then already, this function is not part of the NTDLL but of the kernel 32 DLL, which means that during very early process creation it is not available, and while realistically we can assume that it would always be in any future Windows version present in its current form, because if it would not be, then no other Windows application would or at least almost none would run. So it kind of can be relied on. A more low-level approach is to use calls from the NTDLL, because this is the only DLL which is always guaranteed to exist in any Windows NT process. And so for that, in our shellcode we will be using the mentioned NTDLL instead of the kernel 32 DLL, but so we have here already imported two functions from it, but for this we of course will also need to know which arguments those functions take, and as it is, those functions do not just take a simple address to a C string, but are a little bit more convoluted. So we can find some good source for documentation. This is not necessarily the best. Let's look for that. There's a site which was a bit older, but they had like really everything nicely documented. Because this is just for the. Oh, this is a new site. Interesting. Okay, well, if we don't find the old one, I should have a link somewhere, but for now, okay, then let's go with the newer one. It gives us all the necessary all the necessary information anyways. So we'll copy the two function prototypes here. One is to load the DLL library, and the other one is for getting an address of a exported function. Okay, so as we see with this one, while it contains technically a vchar path, this is, as we see here, it is optional, and the other as well. What really is needed is the third argument, the DLL name, which is provided as a pointer to a Unicode string, and a Unicode string is slightly more complex than just a C string. We can quickly see if we have the right includes to work with it. We do not. What did we include on the Windows? So let's include hashing the inter. Oops, that's not the right. Internal. This one should have a definition for that. Right. So we have here the definition for Unicode string, and as you see, it is two shorts containing length and maximum length, as well as a pointer to a buffer. So if we want to use these NT-native DLLs, we will need to construct such strings in the target memory of our target process, which is not fully trivial. Of course, one reasonably simple approach would be to use additional allocations, so that we then really allocate additional memory for those buffers. So this is one option. We just would use virtual alloc_x multiple times. The other option would be that we use virtual alloc_x once at the beginning, already knowing the size which we need to allocate, and then we would draft everything based on the address that we have obtained. But this is a less it's a less transparent process, and I think the most reasonable option here for us will be to go with just allocating additional memory for the DLL path and later for the function name as well, if we want to call a particular function on the loaded DLL. A hybrid approach would be, of course, to construct the string using the shellcode itself, so that we have so that we provide the shellcode as such only a normal C string, and it would then construct such a object, but this would make the shellcode much more convoluted, so this is not an approach which would be generally recommended, since basically, the long story short is there is no advantage in only having one virtual alloc in comparison to multiple. There might be, of course, edge cases where you can only have one memory block, which would also be let's say solvable. So we could have fixed offsets, and after we allocate one block, then we would just update two offsets inside our shellcode before we write it. So there are different ways of doing it, but for now let's start with just allocating a new memory for this. So we of course will need to do this first, as we want to know the address. So let's call this DLL path address and DLL path and func name address as well. Okay, so this and this. For length, we should generate the length for this. So size t len is equals what's s len of DLL path, and this is in white just, so asterisk c of HRT, and of course +1. We need some space for the terminating null character, although technically we don't, because the way this Unicode string works is the string the buffer points to does not need to be null terminated. It usually, in most cases, is, but that's not something one can rely upon. So if you are writing code and it's just quick and dirty, and you check it, okay, in this use case it appears the API always returns you a terminating null, then great, you can use it, but there might be a change to Windows, or you might want to use the code in some other place, and it is simply not guaranteed that in any case when you are reading some Unicode string from some data structure somewhere in the kernel or somewhere, that it will have this terminating null. It can happen, and I see how it happened, that it really just ends where it ends, and you need to evaluate the length variable and copy only as many bytes, and if you later operate with a C string, then of course add your own terminating 0 to your copy of that data set. So in our case we could kind of save 1 byte, but that doesn't really make sense for us, so let's go with that. And here of course we only want the memory. One issue. Execute, that should be, I think, execute read write, because I do not think write process memory will be happy with writing to a read only memory. So we of course make this read write, and here for this we can just make it read write without execute, because it is just a string. And technically, if you want to be efficient, we could mangle those two together in one memory block. We should do that. That sounds like a good idea. Okay, so this will be for later. Then we'll have here our func name len, which doesn't have a multiplier since it is a ANSI string. Let's quickly check our this one. this one. So this takes the handle to the loaded DLL, like the load proc address from kernel DLL, procedure name, and as you see here, it's not a pay Unicode string, it's a pointer to an ANSI string. And then we have optionally the procedure number. So the exported functions exported by a dynamically linked library can either be identified by export numbers, they are called ordinal numbers, or by a name. The ordinal number export is not really used nowadays much. It does not really have many advantages except that the file is slightly smaller, but then you have of course more ambiguity. So if you have a DLL and you change the DLL names, then or add additional functions somewhere, then you know that they will if the name is wrong, then the export will not work and the program will gracefully crash or just report an error. If you are, however, getting the functions by their ordinal number, technically you have to specify the ordinal number when compiling, so they are not randomly assigned. But of course, it is possible that you decide to change your API, change the numbering to make it more intuitive or something, and then if for some reason you would have a newer or older version of a program loading a newer or older, respectively the opposite version of the DLL, it would load the wrong functions and then create some very adventurous crashes. So the usage of names really has advantages. So in almost all cases, you will not see this usage by name. It's also indicative that the kernel 32 DLL functions do not take any ordinal numbers, they just work by name and that's it. And of course the last parameter is a pointer to an address which will receive the function address if this function succeeds. Alright, so we were here, and of course it's not DLL length and not CSLen, but strlen and path. So we could then, we would here just call this len, let's call this data address, and length is equals then to this plus this, and in principle we don't, and in principle I think we do not need anything else, size t, so we can just stuck to it, page read write, page commit, that's all we need, this can go. Right, and we should generate from the get-go the right addresses which we later will use when constructing the other thing. So address is equals, the one is just the other, it's just a copy. Oops, and the other one for the function name. I'm thinking if we can somehow add a new line somewhere to make it more readable, but I don't really see a nice place at all. Will just be address plus this, but since this is a void, the plus doesn't work. It needs to know the size, so we might go with byte asterisk, and then casting. So we get so after the cast we have a pointer to bytes, so the increment is +1. We increment by, and I should call this size. They often said whenever try to use length for count in word units and length, and size as in bytes. And of course, if we for func name that would be the same, but for DLL path it wouldn't be because here we have a different size. Okay, so data, not SATA. Data size. So we have our size. We have this. We add size in bytes. Then we are pointing to basically behind this one. Behind this terminating 0, which is great, and that is all we need. And now at this point we can already write to the target process, since we already allocated the memory anyway. So one is this address, the other one is one is this address, the other one is that address. Lengths we already have computed in bytes as well, and here we have just our two pointers which we cast. For production code, we would of course for production code we would of course evaluate the return value of write process memory, and if it fails, then we would terminate. Also here we would check whether this allocation was successful, and if not, we would terminate and so on. But since this is mostly a proof of concept, we will not be spending our time on adding error checking. If you want to use this code later on in some of your own projects, you can just add error checking where you see it reasonable to do so. Okay, so we have this data, we have this. And what our plan is, we have this data size parameter, which we can now set to whatever we want, and this gives us inside the shellcode a local data area which is relative to our current position. And in this data area we will want to store a few things that will be needed. Let's think what we will need. Well, we will, so we will need a few things. One thing is we will need a return address, which is what we are getting here. So pretty much the address to which we jump. Let's write it here. To which we jump after the shellcode is done with whatever it was doing. Which you would be in this case the entry point of the application, the normal entry point of the code that later we'll call the main function and so on. The next thing we will need here, so this would the addressing we will think about later. The next thing we should think about now. So let's say it's data 0. So after the address is 64 bits, so we will have here 8. Now let's go with this plus 0 plus 8, because we have like the counting here from the beginning of the shellcode, which starts at 0, but then kind of it actually would be at 6. But we will try to design the code such that we would have that we can use these numbers, and it will internally. We might actually need to introduce another variable. Data offset. Oops. Data is 6. Well, the data offset is undefined, and we define it here as data offset is equals. And so that we get 6 out of this, we can take. What do we take? We take this one because this grows. Minus this one. This should generate 6. Let's write. But if we change here, for example, we add, we decide we want to add another knob, or we decide we want to remove our interrupt, our break, then the things will shift, but then this will also shift, and the whole idea is that we make the thing somehow shift proof. We have the code here. We have where we jump to. Jump to data size, right? And here, since it's a relative jump, it re-jumps by data size. It doesn't care where in the shellcode it is. It just adds jumps incrementally. So this can stay. We have our data offset, which is 6, and we have now plus 8. Okay, next thingy. So we have where we want to return when we are done. The next thing we will need is we will want to communicate to the. So we need at least some information in our shellcode. Even if it's a very low-level shellcode, there to some extent might be ways to make it even more independent. But since we don't want this to be too complicated and too convoluted, we'll give it a few informations which we can easily find out, like these two addresses. So, as I think I mentioned already last time, while the address of load library W is not, it's something we can kind of rely on to some extent without actually having the a proven correct address. We can just assume that it's the same as we have. For 32-bit processes, it's difficult to obtain, and so on. So here, since this DLL, the NTDLL is loaded, is mapped into the process, really at process creation, even before any code in the process got executed, or in the NTDLL itself. After process create, even with the suspended flag, we can use a query memory information. What's query process information? One of the query information functions of the NTDLL to get the memory layout of the just created process, in which we will be able to find the offset of the NTDLL, and if we parse that memory, we could also then extract these addresses. So even for the use case where we would assume that for whatever reason they would not be the same as ours, but realistically they will be the same. They must be. They not must, but practically they will be, because it's the first thing ever loaded. So any other DLL, even if it would want to load its address, will then be relocated, because there is no mechanism how a already loaded DLL can be relocated. A DLL can only be relocated to a new base address while it's being loaded. So these addresses are, for every practical purpose, very reliable, and this is why we will just pass them here to our shellcode. So LLD, or let's use the full name, load library address. Here, let's get rid of the underscore, and here it's clear what it is. The next one will be, of course, the LDR load procedure call address, and this was capital, be correct with the nomenclature. So we have those two addresses. Then we will need the path. Right, and of course we need to so this then plus 8 plus 8 is 16, and plus 8 is 24. Right, so next thing we will want to have will be our Dingsbumster. Actually, we maybe should change the order. Let's change the order slightly. This we'll add later. Here we will add the Unicode string. So let's write DLL path Unicode string, and this is a good question how big this is. I think it's 16. Yes, it's 16. So 16 plus 16 is plus 32. And with only this information, what we could already do is we can retrieve the so we can load the DLL and retrieve its base address. So we could call load DLL. So here we will reserve some space for the module. So load the DLL base address. That brings us to plus 40. Then we have our loader get procedure address. Then we add another 16. Wait, so this adds 8 plus. Then we add another 16 for the func name. Actually, let's go with these names here. DL path Unicode string, and it was func name. Was it with the 2 i's or 1 i? I don't remember. 1 i ANSI string as right. Let's capitalize this as Unicode string ANSI as ANSI string. This adds 16. That will be, what will that be? Probably 64. And this will return us again an address. So it will be the function address. That is plus 8. This gives us then 92. That might be all we need. That will be all we need. Yeah, good. That will be all we need, I think. And now we of course need the offsets to define them somehow. So what we can do is can use defines. Or we could be more dynamic about it as well. long data pos is null. Of course, here will be const. No, const is not good. Let's just go with. No, we could go with const. Let's go with const. Const. So the first one is return. Let's write the whole word. Return address offset is equals data pos plus ist gleich. We cannot plus is gleich. This cannot be const, but then this won't be happy being const either. I think we can see. The thing is, when you use const, then it will often default to just calculate the value and then use the value. But yeah, let's go with that. We will see if the compiler likes it or not. Zack. Yeah. Okay. So we have our return address. And it's not plus, but plus is equals 8 of course we said. About some. Okay. The next is the loader address. Then const. Long and yeah. The LDL offset. Equals data pos and data pos plus equals. Alright, that we should keep plus 8. This comment we should keep because this also is just plus 8, but effectively this puts us to the plus 16 position. Next one here. We'll copy some of that copy. That's the DLL pos offset. That is not consistent, and then let's make it like this. That everything looks the same. Is equals data pos. Data pos is plus equals 16. The nice thing about this approach is that even if we that we can avoid miscounting, and it also is then easily editable. DL base or base address. Washed. Data pos plus 8. Here we then have our offset data pos plus 8 again. That's correct. That gives us 48. Disk plus 16. Func name offset, and the last one function address plus 8. Technically the last plus 8 obviously is not needed because we don't use this, but if we would need, for example, to know the size of the data, we could actually use it. We could now write data size is equals data pos, and we would have a really nice non-wasteful memory alignment. But this was then func address and the other base. Let's just module. Let's leave it at the area base. Function address. Then the whole thing should be 92. And as mentioned, we could now actually just drop the. We need data size here for the jump, so let's leave it as is. Well, and also we had 92 and we have allocated 100, so we could have a check here. The data pos must be less or equals data size. I'm not sure if we actually have the right includes for assert. We don't. So if data pos is greater data size, then do we have a return false? Return 0. Fail. Oops. So we can use this for error checking. And yes, the other option would be to remember this address and then write to this address after we are done assembling the data. Maybe this is even better. Let's do it this way. Data size offset. We have the okay. Let's maybe do this way. Yeah, that's this nicer. So here we just kind of so we write this as equals, and this must be a pointer. So it's a pointer, and then in this, then let's call this p data size. That's a good name. So right, p data size is equals, oops, this much. So this already moves this other pointer further, but here we save the old value p double word head. Oh, and since this is defined as double word, which is the same as long, we can here use we should use the same type just for correctness. Then of course this goes away, and asterisk p data is equals data position, and this is then shifted by this amount. So we can either dereference the old value, or we could use again data pos. Does not really make it. Let's go with this. Right, so we have shifted that to everything. We don't have any collisions. We could actually maybe add here a dummy wint8 to have at plus 100, so that we have nice values per spare keyword or reserved. That doesn't matter. So we just shift this by 1, and that's it. Right, and we have the offsets, but we have not written yet to them. So this is something we could do at this opportunity. Data offset. If we want to do this at this opportunity, then in principle we could just use our writing mechanism, and then we wouldn't need this assignment because we would have incremented all the other things as we go along. So let's do that. Okay, so first one is the address. So we have here our... do we need data offset then for anything? We will need it later, yeah. Let's skip that. So we go with our code. Asterisk code punct keyword plus plus is equals return address we have here. Suck. Here we have loader address. Then here we have a to do. And there we will have a to do. And technically this is nicer to do it in this order. Doesn't matter. Does not matter. Here of course it doesn't want to cast void asterisk to a integer. We need to tell it that it's fine to do the casting. Right, then DLL base, this will be 0. This is an empty, not yet filled. This will be dynamically filled while our code executes, so we will be writing to our shellcode ourselves. That's why we will keep it writable, even though that's not the safest thing. And for here, we add the address, this one. Zack, ANSI string is another to do, and then this thing is another 0 because we have not yet filled it in with anything. And if we want to have a spare 0, then we add here another 0 as well. Good. Then this can go away. And now we need to construct this. So to make this more transparent, we will grab those two structures and put them here so that we can see what we need to construct. So as you see, we have a short, then we have the buffer, and effectively on a 32-bit system, this would be really how the structure looks. On a 64-bit system, however, the thing is that there you have 64-bit pointer alignment, so it will add. So let's maybe hack this a little bit. First of all, we align the names, and then we just add _64, so that we know that we only are looking at the 64-bit version. And there you will get here a ulong empty, which is just empty. It doesn't hold any data, doesn't have any function. It is just there such that the buffer will be aligned to a 64-bit boundary instead of spanning across two 64-bit keywords. This improves the performance when reading and writing from RAM, because the CPU then can just make one access instead of having to do two accesses, and maybe even wasting two cache lines instead of one. So it's a small optimization, and you can in fact turn this off. But obviously, as soon as you are interacting with structures of libraries which you have not compiled yourself, then you have to adhere to whichever sort of alignment they chose, and the default alignment is the one shown here. So thinking how we can make it even nicer, but we cannot. Like I mean, we could maybe open this on the side, so that we at least have some. Yeah, so then we see we won't be editing the system file, just so that we have this here to keep an eye on. Okay, so our first Unicode string. So we have here our assembler thingy. So p word, because a short is a word, which will be length in bytes. This is called length, but in fact it's in bytes, not in words. We have here our path size. That's annoying. Okay, let's edit this. So we need this without the +1. So we will scrap the +1 here and make it plus size of vechar plus size of char. And then when copying, we want to keep the terminating null. So we will add this here and there, so that we have our terminating nulls in our memory block. But these variables will be exactly what here is expected to be needed. Right, so DL path size. We write here the DL path size. That is, we should write this down so that we know, so that we keep track of things. Unicode length. Now the next one will be max length, and here I will just go with size +1, or rather plus. In principle, length and max length would be exactly the same. That would be fine. But since we have this byte, let's just put it there. Double word is our placeholder. It's just 0. And then we have a keyword. We need a cast like there to the address. Here, DLL path address. Zack. Okay, and that should be our right. And here, I should add those as well. So this is then empty or padding. Let's call it padding, because that's if you would be searching in the internet for this mechanism, the proper thing to search for is padding or alignment, but padding is a better word for that. Right, and here we have the edge, buffer. Right, now we can more or less copy this one-to-one. For this to do, we just, instead of path size, we'll use func name size, and the few other things will be others. So this and this, is just char. And of course the last buffer needs to be this one. And of course here we will change this to ANSI string. We had 64 in the name, so we should maintain this. So we could align the comments so that this looks a bit more readable. So that small things like proper comment alignment actually help readability of code a long way. It's good to do that. Zack, 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 zack. Okay, then now we should be func name, func address plus char. That looks correct. That looks right. So we have created everything we need, I think. Good. Okay, here. Right, and before we proceed with the rest of the code, let's run this again and see if we really jump to this in 3 again. So let's see if this enabled. Yeah, okay, then it should be reasonably easy. We just run it. That's our main function. Then we end up in our first view disassembly. Can drop that here. Right, so we have our C. Then we have our jump, and here we have some things, still have a lot of zeros. We can inspect this actually here in the memory tab a bit better. Something is wrong. We did not we have too many zeros. We didn't write something, or it should be okay, let's get it. Alright, so we start with our code here. And at this point, let's put a breakpoint here and inspect. Oh, actually, might be it is correct. Maybe I was too fast with my judgment. ISC. That looks so little. That looks too little. Oh, I know why. I know why. Damn it. Here. We of course need to increment those things. Right. Let's try again. Then we are here, and you can check data pos 80, but it's wait, it's without hex. 80 is not good. 80 is too little as well. Where did we forget? So we started 0, 8, 8. Sorry, here. Q, what, double what, Q. Q. That should be right. Oh wait, but that was for this one. Let's run it again one more time. Why would we have here too little? But this is the one where we use the plus, so let's count. Let's be lazy about that. Calculator. So we start at 0, we make 8 plus another 8, that should be 16 plus 16. Should be 32, that's fine. Plus 8, 30. Plus 8, 38, yeah. Plus 16, 64, this is also correct. Plus 8. Oh, that's where we miscounted. 72. And then 72 plus 8 is 80. That is fine. So for some reason I screwed that one up. But now we have now it's consistent. Let's inspect the memory if it looks properly. Oops. Comma shouldn't be there. Still looks a bit too many zeros. We can actually step here, two steps to see what changes. Oh wait, did we change something? No, we didn't. Right, we changed one offset there, and then why are there so many zeros here? Should have 16 zeros. Oh, that might be correct, because we have one address here, and this is probably the other. No, this will be the other address, and then we have one address. That might be enough. Okay, it probably is correct. So let's run it fully, and then let's see whether we jump where we want to jump with this assembly. So we are in our first break. Then we go step by step, and then the next step goes directly to the next break. So we end up exactly where we expect, and then we would be executing the NOP instructions and so on and so on, and then at the end I think we added another C to end it, and then a NOP, and then the rest is just uninitialized memory. So our data section looks correct. We could have inspected the paths whether they were written, but I will just assume that these functions didn't fail. Okay, so we can start with writing our code. Do we have the right alignment at this point? Here we are at plus 80, but this is of course not the whole thing. Then actually we are at plus 86. So this effectively would bring us to 86, which is not properly aligned for a function call. So the thing is that with the 64-bit calling convention, when calling a function and preparing the stack, there is an expectation how the offset of the stack is set while we are doing the function call. But this for now that should be fine. Let's or we could add a few more dummies. I mean, let's go with that. That just to it would make it pretty, but it would make it less compact. If we just add the re-add the data size variable and just add 128 or something, that will give us the right offset. Let's ignore that. Let's for now just go with the with what we have done until now. That should be good enough. Okay, so we have our entry point, we have our things. Okay, so the first, so let's remove this breakpoint here. The first thing we will want to do before starting to do more complex things will be to save the current state of the CPU. So you would of course want to avoid the need to, or rather we would want to avoid overwriting registers which might contain informations which are needed later on by the actual entry point. Of course, we could here select a function where we know that it does not take any arguments, so we would be kind of free to break some of the registers, but then we have another problem, that is that some of the registers are defined such that if one uses them, one is responsible for restoring them before one returns. So and then since we are calling functions of Windows, we don't necessarily know what they will be doing, although they should restore it properly. Anyhow, long story short is, for our own operation, we will want to save first all of the registers of the CPU, or at least all the integer registers, to the stack. And then we can call all the functions we want without any issues, and then just before we return the flow control to the return address, we will just restore all the registers. And let's do that. So first as address code punkt pb ++ is equals, there is this instruction push f, which assembles just to this, and wait, is this the right thing? It is the right thing, but that's not what it should be. Usually push f should be just 9c. Why did it add the 66? Well, if we disassemble push fq, Okay, then we want to use push FQ. Yeah, it's when it says so. Then it's push FQ, not just push F. So this is 0x. What did I say? 99C. And this is the push FQ instruction. Though I'm pretty sure when we look in the debugger here, it will just call it push F. What it does is it really pushes all the floating point registers on the stack and increments the stack pointer accordingly. So this gives us already some things saved. We probably don't need to do that since we are not using the floating point registers, but since we can do it with just one instruction, why not? And then we are on the safe side. The next thing, but as mentioned, we most important want to save the integer registers, and there the problem is that we won't save all but one because we don't want to change the stack pointer while doing our saving. So we will save them one instruction at a time, and we will be using the push and pop instructions. Push, for example, so push x is this one, push x, what's that one? X, no, that's x, bx, bx is the other one. So as you see, they are all kind of the same, just that there is some numbers inside the bitwise representation are changing. So since we need to do this 16 times, we will just create a loop that will write some code for us. Size e, size t, e is equal 0, e is less than e is less than 0x0f, so it's less than 16. That's the count of integer registers on the x64 platform. Okay, and now we do not want to save the stack pointer, so if e is equal 0x04, it's the fourth, it's the fourth register, so if it's the fourth, and it's 2 equals, the fourth register, then we continue. So skip saving RSP. For this one we don't create, then we need, so the way the x64 instruction set was designed by AMD was that they just took the x86 instruction set and just extended the registers plus added twice as many registers. But the problem was they wanted to keep the instruction set as similar to the original one, so for almost all operations which relate to the second half of the registers, you need to have an additional prefix in your opcode which indicates that you are using one of the new registers. So if I is greater 7, so 0 to 7, from 0 to 7 inclusive, these are the standard 32-bit registers, and you can address them without this additional prefix. But if you address the 8 to 16 exclusive, 8 till 15 inclusive registers, then you need to add this prefix address code .pp ++ is equals 0x31. They are, if I recall correctly, more than just one particular prefix, but for this operation the 31 prefix is the right one. And then it's actually quite simple. We remember x was 50, and in fact the next register, so if we just take the value and would put 51 and disassemble that, it would just push RCX. It's not like ABC, but rather ACDP, I think. No, not quite, because at position 4 then you have this RSP. So it's not very intuitive, but it is what it is. So there's code .p double word, no, sorry, per byte, and byte plus is equals 0x50, and then we just byte-wise add to this I or and it's not end, and 0x7, so 0x07. This is a bit mask where the lowest 7 is 3 bits. The lowest 3 bits are all set to 1, so we just take this portion, and if we then do the second half of the loop, then we add this prefix, while we just use here the same opcodes as before, just with the prefix indicating that it is acting on the other register. So let's here say you will write what we do. We do push stern stern. That's it. Okay, and this, as mentioned, generates the whole code that we need for us. Good. Then what we want to do here is we will want to reserve some stack space for our operations. So we have save. Let's add a comment. Save on registers or CPU registers. Now, next thing we want to do is sub rsp 0x38. So we want to save some space. 0x48 is in decimal. I do not remember. Hex 56 bytes. Okay, then we want to save to have 56 bytes to play with. Then we can just take the code to our online assembler and nicht ref but rsp rsp. This gives us, so if we fix this, then we go there and we grab this. Okay, that's a double word, so let's just go code that dot double word plus plus is equals, wait, is it double word? Yeah, it's double word 0x, and then we need to reverse this 38 CE 8348 should be right. Good. So we have registered something. Now let's prepare our call to load DLL. So prepare arguments for this. Okay, so this would be now helpful to see the arguments here on the side. We should just add a text file to the whole project. Add new item just add a info text which we can open on the side, and there we just copy those things so that we can keep an eye on what we need to do. Okay, right, so we reserved some space. We are now preparing arguments, and the way the arguments, so we need to prepare for arguments. We need the return handle that will be this what's the first zero, this one, DL base offset, and then of course the other one. So the way the arguments are passed to functions on x64 is that the first 4 arguments are passed through the registers RCX, RDX, R8 and R9, and the rest of the arguments, if we would have more arguments, would be passed on the stack, but luckily here we only have 4 arguments, so this makes it a little bit simpler for us. And the next thing to know is that if we would have the arguments on the stack, then they would be in reverse order. So the first argument on the stack would be the last argument in the function call, and the last argument before we call the function on which would put on the stack would be the argument, the first one within the function call. So since we here are actually using only registers, we don't need to care for the order, but just for pedagogical reasons, let's maintain the order. Or maybe not. Let's keep the normal order. That will be more intuitive. Let's go with this approach. So the first register, as mentioned, is RCX. So we have to move RCX, comma, and then we need to move there. Well, the first one is what? The first one is PAW string the alpha. That's 0. So we just move 0. We don't care for what this will be 0. Maybe we should first write the comments. RDX will be 0 as well. R9, R8, sorry, R8. R8 is now the important one. This will be the address of our Unicode string. So R8 will be, it will be a different command. It will be a load address layer R8, and here we want the instruction pointer plus something. I will think about the something later. And for the other one, R9, it will be also a return instruction pointer plus something. And then of course the last thing will be call instruction pointer plus something. So the pattern starts being apparent. So let's start with the simple ones. Zack. So as you see, this is already a bit longer. RDX will also not be as short. It will be identical, just one bit will be changed. Okay, so let's do it in reason break. Code.pw plus plus is equals 0x C7 for 8, and then we make a byte. Byte plus plus equals C2, no, C1, sorry, 0x C1, and then p word is 0. So as you see, we have here a lot of zeros. The other one is identical, just that C1 is C2, and the layer, and then now we need to find out the right value. So for demo purposes, we will just add here something we can easily see, like let's see 0x 77 bbccdd, and we'll just put this here everywhere, this pattern, and we will assemble it. So this gives this. This will be identical but 1 bit again. This one will be something completely different because it's a different different opcode, so it compiles to something different. Okay. Yeah. Okay, so we have here a pattern. So the structure is kind of the same. We also have 3 things, and the last one takes a value, just that here it will take something else. So here this was 8D for C. Here we have 0.5. The other one will be 0D. So here we see that one is 5, the other one is D, so 0D. This will need to be added as well. And here now it might work or it might not. So the thing is, the value which we need to enter here is the relative offset to the current position in the code where we are, which we are executing right now. So this will be our data position. We need a relative position, so data position is not relevant. We need the first address. What we are interested in, this Unicode string here. So we'll be using this DL path offset, which points to data position. This is not fully great because it makes things more complicated. We have data offset that will be essential. Data offset tells us we need to calculate first we need to calculate the difference from where we are to the base. So and this will continuously change. So let's define a helper macro somewhere. Base. Let's call it base. And this will be, what will it be? Code .byte minus, and then we can let's call this database. This will be minus our data offset. Okay. We take the negative of that, and I think, oops, we need to add to this, subtract from this size of double word. This should give us the one. The position, gives the position start of the data, so gives us the position of the start of the data section from the current instruction pointer. Okay. That will first be a negative value. So first let's add the offset. It will be negative in any ways, doesn't matter. So let's just start with base plus. Which one did we want? The DL path offset is the right one. DL path offset. Okay, it is not happy. What is data offset? Data offset is oolong, that should be fine. Right. Base. Oh, we are right now. No, that is not correct. We don't care for data offset. We will care for data position. Dash 10 data position is like this. We don't even need data offset for anything. We might not need it at all. Let's comment it out for now. Right, it's more elegant if we put those things here. Data position. We already used data position. Address. It's not well. It's close enough. Pointer. That's good. PTR. That's not used yet, and it's correct semantically. Right. Now it should be correct because we have pointer in bytes. Means pointer in bytes gives us a number. It's like with units in physics. You need to the unit cell right, then it works. Okay, the other one just uses the other offset, which is the DLL base offset, because this will be the return value. And in both cases we want the addresses. So one takes the address of the Unicode string, the other one takes an address to a pvoid variable. Okay, then now let's look to implement the call. The call, as we see here, is nicer. It's slightly short. So wait, oh, that's not right. That should be D. That should be D. That should be D everywhere. Oops. Right, now it's correct. Okay, let's be lazy. This one goes away, and here we get, what do we get? 15 FF. And then we have our DL base plus 200 DL loader offset. Okay. Good. So at this point we have called the function, we should have gotten the right value back. We could try this out. Maybe it already works. I mean, it should work. It's. I think we didn't do any mistakes, but as you see, it's really easy to make mistakes with this sort of work. Okay, so we are here. Let's take this there. Okay, so step by step. So we have our jump. Now first we have our int, then we have our jump. Then we have the push. Okay, it's push FQ, it's not just push F. Then we have here the instructions assembled by our loop. Let's quickly step through them. Then here we are reserving stack space. And let's see, we have move, we have, no, that does not look right. So we should have move RCX with pluses are missing here. We did not shift and then we overwrote. That's not good. No bueno. Okay. Next try, next attempt. Continue. Show disassembly. Right. Let's put again this here so we can see what we have. Because I said we will be, one of the keywords here will be overwritten by the DLL. And we will already enter DLL main. We can put a break. We already have a breakpoint there. So actually, while we step through this, we should arrive here in this function already. That is nice. Right, so we jump, then we execute those things. Then we prepare the stack. Okay, let's see. RCX, RDX, and then we load some registers. That could be right. We can take a look there. Debug, window, memory 2. Okay, so we have 80, 82, that sounds promising, and we have zeros, and we have an address. So this really looks like it's a Unicode string address. And the other one is just all zeros because we have not filled it with anything. That looks great. Okay, so let's step, 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 step. And if we now make a step, we just step in. So we do a step over. And it crashed. Oh, I know why. I know why. This is not the thing. Is the lower LDR load DLL function? It takes a path in so-called NT-path notation. It doesn't take like the normal Windows path where you have a triflet and then the rest. But it takes like backslash device backslash hard disk volume number backslash and then there is the path. There is, however, a way how we can cheat around that. Because if we have let's see whether I can see the device path somewhere. No, we don't. I fixed it already. I had a bug that it was showing those paths, the NT path, but it does not. So what we can do basically is we can prefix the path with backslash question mark backslash, and then it will work as a NT path without having to resolve from the drive letter C to which device hard disk volume number it is, because this is dependent on the system, so it's not the same in all systems. Depending on your partition layout of your of your main hard disk, this will be a different volume number, so we cannot hard code this, and resolving this would be a bit too much work, but we can use this trick with this backslash question mark backslash to achieve this. So here for the DL path size we just add 4 times, actually we could do this differently, Stern, no, just double T, QQB is equals L backslash question mark backslash. So what's len plus what's len. Right, this needs to be this. Or an asterisk. Selected. Okay, then let's go for asterisk. Right, and remember, then we have the right process memory, and then we will here need to add a second call. So we have DL path. Here we only have then then of this. And here we pass this, so we only write this thingy. But the DL path then already contains this path size. Yeah, but this value we want to keep for later. So here we'll go with taking this. Oh, that's not good. +1 times. +1 times this, and here we'll go with resolving, with getting the length of the other thing just again. So again it says length +1, but here we need to change the address to, should make the address here another address. Was alright, and we don't want to write here this one. We will be overwriting this in a second anyways. Right, wait, what is not like it about this? Yeah, this needs to be casted to byte. Right, path size is with the whole thing, so that should be correct. Then we have the address 2, to which we write the DLL path. Again, we just take the length, but this time we make +1 because we want to write the 0 as well. It looks correct. Okay. Let's try it again. New view. Right, let's put a breakpoint. Wait. Right, first we need to make this jump. Now let's put the breakpoint on the call here. And we said that this is the address of our Unicode string. So A0 1 2 3 4 4 this 8 should be 8. This will be then the address of our. Let's open another memory window. Window memory number 3. That does not look right. Oh, that also might have been the problem, that we just had the wrong address from the get-go. Wait, so one. Let's group that in something reasonable. 16. Right, and if we start here, so we have 1 2 4, then we have 1 2 3 4, and then we have the other group. Okay, but this apparently did not resolve to a valid address. We tried that already. Why did it? Nope. Okay, then we have another problem. What did we do wrong? We have here the addresses to which we are supposed to write. We should print those just for testing. And this address we have put here as a keyword. It should be right. So let's just put a breakpoint here. Continue. And let's print out those addresses here so that we have them at our disposal. Right, and this is the same as the allocated one. And the first one is the same, the second one is slightly further by 8, right? Next one is significantly further by 88. That looks correct. These addresses looks correct. And let's quickly take a look on the registers. The last, wait, AX 1, yeah, 1 is okay, that means success. And we have here written the LPath address into our shellcode data section. I did not press the right key. View the assembly. This time it went past it to the other breakpoint. Let's compile this DLL so that we have a new version of it, because if it is new, well, at least it didn't crash anymore. Let's try it again. Suck. It might still not have worked as we wanted it to. Right, now we need to redump all the addresses. Let's just go with the only one we are interested in right now and don't care for the rest. Okay, now we have the breakpoint. Now we go to view. Now we go to one step further. And here we go breakpoint on call. Continue. Okay, let's try it again. So memory 1. We go there. Oh no, that's the wrong one. This one. That does not look correct. Looks like it's all zeros. That should not. Sorry, it's the wrong address. This is the right address. Right, that looks correct. And then we group this again by 8. Sorry, by 16. And this should be the address But it is not. Why is it not? It is completely wrong. So we have our address. The address must be what we allocated, and it should be just written here. Did we forget a plus plus somewhere and overrode something again? Doesn't look like it. Okay, let's put a breakpoint here. Run it. Continue. Clear all. So again, this is now the right address. It's annoying because it always changes each time we do something. Then we have here a DLL path. So we have here, we switch to hex view 88 and 88 plus 2, that will be 80A. We can go to there. -8. But not in Q, but in B units. Right, so we have our data written here. Now when we do the step, it should write that is, wait, AC, A3. Right. This is of course byte reversed. Okay, but we know what it should look like. That was a mistake. You cannot like copy it from there. You need to replace every single pair. You need to reverse the order of every single pair of the values. That is annoying. But let's continue. Okay, so view step. Okay, so one more step. Push F, call, continue. Again, we go here and we compare it with what we remember that we need to reverse, and when we reverse it, then it looks fine. Then we can also check whether the reversed address is fine and it contains, as it should, backslash question mark question and backslash C double point and then the rest of the path. Okay, so let's put the breakpoint at the very beginning of this thingy and look for the registers and do a step over. It returns an error. It doesn't load the DLL as it should. Why? Doesn't matter, just let's go to any of those. It returns the error DLL not found. Then it doesn't like our path. For some reason it does not like our path. I'm pretty sure that takes NTDLL paths normally. And the thing is, there is not much documentation that always took the anti-path. I'm pretty sure of that. This here. It just tells you flex and DLNA, but doesn't even tell you which path format this thing should take. They are trying a normal DOS path. Did we fix something else in the meantime? Let's try it with a normal DOS path again. Maybe it is fine without the. Maybe we don't need that. Actually, for simplicity, we could just make this an empty string. Then it will just give us the DOS path again. So, okay, so we can start here. Then we have our address which we want to save. Then we continue. View disassembly. Step. Call. Continue. Then we want to see inside this process at this location. Okay, now we have the proper path. Okay, let's see what it does now. Right, registers so that we see whether we get an error code. Now it just crashes. That is mildly annoying. I mean, that would suggest, because it tries to do something while in the other case it just fails outright. This value here was correct because it was just pointing to our empty, and it's writable, right? Read write, yeah, it's writable, writable area. So it must. Maybe the stack alignment is wrong. We sure that this is correct. We want 38. Okay, let's remove all the breakpoints we don't need. We will assume the path is correct. We'll assume it takes a DOS path for now. So let's simplify this back to our previous version. Yeah, +1 then. No, +1, that was the thing. Here, this goes away. And this is just +1 times WTRI. Okay, then we are back at our simple version. Now this is readable, and before it just didn't like this, so that should be fine. Let's just run it again. Check if the stack alignment is correct, and this breakpoint can go as well. View. step, then we go to call, and where's our stack pointer? RSP. Doesn't look wrong on the first glance. Let's see. Wait, might look wrong. Right over here. Okay, so we didn't save one of the registers, and that broke our stack alignment. So here we had just less than, but it should be less than equals. Now it should work. At least work one step further than the last time. Okay, so let's continue. View. Step. Call. Breakpoint here. Continue. Okay, now let's see our RSP. Now that looks much better. That looks like this is correctly aligned. So now we make a step over, and we end up already in our load, in our DLL's main function, which does something. And then if we continue from this, we end up, what do we end up here in our code in the, right, we ended up in the C, and then we crashed because we didn't have anything else to do. Let's just quickly try it again. Just remove this breakpoint for now. Right, so zack, view, step. To put this here on memory 1. There is our data block, so we'll see as it loads the. When we step over, we should see where it loaded the address here. It loaded the DLL somewhere into the memory, the reasonably high address. So that's the base address, and now we can compare this to here when we in the task manager look on the loaded modules, then we should have our hook DLL, and we have the where we have here its base address, and yeah, if you take into account that we need to swap bytes and so on, we see that it is 917B and so on and so on. So it is loaded here where it should be. So our shellcode now works until this point. The thing with this stack alignment is a very annoying bug, because as you see, we were like 3 calls deep inside the load DLL function, and only then it bugged out. It didn't bug out on the call itself. So in this aspect, for example, the ARM64 instruction set is kind of much more user friendly, because it bugs out immediately. If you have the wrong stack alignment when calling a function, then it will bug out instantly, instead of just causing some weird issue much further down the line. But okay, so let's continue. How much time do we have? Not so much time. So maybe before we now modify everything to load from the so load the really resolve a function, we just leave it for now at the mechanism where it's just entering in the main function, and that's it. and we will just finish the part of the code so that the program then can actually continue run. So here will be a to do. Resolve exported DL function by name and call it. And for now we will just add the continuation of the normal execution. So first thing we want to do will be we want to reset the stack to what it was before. So kind of take the same thing here, just instead of a subtraction we do an addition. So it's add RSP something something. The peculiar thing about the stack is that when it grows, it kind of grows in the opposite direction as you would expect it. So you reserve memory in lower addresses than what you are right now. Okay, so this is our other operation. How was it here? And of course we need to do everything now in the exact reverse order, so let's see, this should be quite similar. 8-4, 8-3 for C4 instead of EC, and then 3-8. Yeah. Okay, now can copy the loop to restore the registers. Let's copy the whole thing just again. So let's keep restoring RSP, and the prefix remains the same, but the operation is simply 5-8. So this is now pop. Pop max is 58. So voila, and then this will be of course pop pop FQ. That is 9D. This takes care of all the integer registers, all the floating point registers. And now the only thing we need is we will need to jump to our return address. So jmp to ep plus something. Let's compile it. Okay, and it's kind of like the call. Just that here it is 25FF, and the address will not be the LDR address but the return address offset. Done. That should be it. We can now, we don't need the knobs. We can just keep int client and knob at the end, so that if this, I mean, this will not fail. And if it fails, then it will crash. There is no way we can run past this. So this is just here now for as a placeholder. It will not be executed. Okay. Maybe we don't step through it. We just check whether everything works. And it crashed. Okay, so something is not quite right. Wait, so we redo this, we restore those, all of them. 9D was correct, doesn't matter. Okay, we need to investigate why it crashed. Maybe we have something about the return address is not correct. We have it here, we wrote the right address, that should be right. Okay, so restart this. Return address looks like a real address, so let's see. Let's continue. We end up in our break. We did assembly. step. Now we know that it loaded correctly. Add RSP, pop up, that looks right. Let's be courageous and put a breakpoint here. Okay. So at this point again we have successfully loaded our DLL. So that worked. Let's see if we have a real value there. This also looks like the right return address. So if we go there, yeah, then in the thread start routine, and we crash with a null pointer exception. Okay, so just to debug this, what we can do is we could just comment out everything. Yeah, from here to here. So now we basically just have a shellcode which starts, throws an exception. Sorry, if triggers a breakpoint. Here it starts, triggers a breakpoint, jumps down here, and then jumps to the return address. That should work. We're not messing with anything else, so if this also fails, then we have some other issue. This can be continue now. Disassembly, no, so step. Now we have the other jump, which brings us to the actual entry point. Let's continue. Yeah, and now it works. So we are breaking something. With our code. We broke something and this is not good. So let's just check if saving and restoring the registers is not a problem, because since we had a bug there, it's likely might have a second one. Right, so we have registers, subtract. Yes, so we subtract, add, so this should restore everything. Wait, are we sure we don't have a typo here? 38 C4 834. No, that looks right. It's a double. Okay. Will not make a difference, but just for our looks. 50 58. Was it really 41? The prefix. Pop R9 41. Yeah, the prefix stays the same. Well, let's try it out. Continue. Review. Step. Now we have a lot of steps. Right. Yeah, okay, we steps push, add, subtract and add. That looks correct. It should just end up with the same. Oh, wait. Copying the loop was the mistake. We should not have done that. That was really stupid. As I said, we need to do everything in reverse, but the loop of course does it in the same order. This is very not right. Right, and this is minus minus. And since we have s equals 0, this needs to be an int so that we can accommodate for one negative value. Let's change this here as well. Yeah, we kind of just restored all the registers to the wrong registers. That was obvious that the thing will not be able to run this way. We destroyed kind of everything. Let's run it again. Okay, now let's be courageous. I will just start it. I will go past this and okay, we are well better, but not great. Let's run it again. Right, run. View. So we have here our code. We step through it, and we have racks until 15 and sub, and then here. Wait, and then did I not uncomment something? Oh, wait, that is of course this of course needs to be greater or equals 0. We just now didn't do this code block. That was not good either. Continue. Disassembly. Step. Okay, so push arcs till 15. Sub, then stuff, then call, then add, then pop 15 through rex, pop fq. Now that looks correct. If we run it, yes, we entered the other main function of the other function, and it's working up runs fine. So we see our hook is working as well. Yeah, so as you see, it is writing shellcode is a really error-prone procedure, but it gives you a lot of flexibility because we can more or less do here whatever we want. We can call as many functions as we want. We are not limited to a particular argument scheme. We can really do whatever we want. Okay, and we have now proven that it just takes DOS paths, which is odd. Normally, most of the NTDLL API takes actually NT paths. That load DLL takes a DOS path is unexpected, but apparently for whatever reason they did it this way, and I just forgot because that's not the first time I write this shellcode. Okay, and yeah, we have 15 more minutes. We can try to finish it. Maybe we can cram the 15 minutes in here, because it's not that much more than that is missing. So we need to now just call this function. So let's see what we need to do. So here will be arguments for. I mean, what would be extraordinarily reasonable thing is to here at this place check for error, and if there is an error, and if end on error, jump to the end, so that if we fail to load the DLL, the program would still start up just without it, because otherwise if we ignore the error and then proceed with load address and then ignore the error, at some point we are just calling a null pointer, and this will crash. But well, let's see. The thing wants first our so the first argument for this is the DLL handle, so our DLL base offset. So this will be a move RCX, comma again our placeholder. That will be something. Then the next one is procedure name. That will be the ANSI string. So this will be RDX with something very similar. And the other two, one will be 0. So the procedure number will be 0. So that will be move R9 comma null. Sorry, R8 comma null, and the last one will receive the address of the function, of the exported function on success. So that will require leer R9 comma and then again something like this. Zack. Okay, and then once we have this, we can just call the function. Which will be something like this. Just that here it's function address offset. This is the correct call. Should be. Now where did I copy this from? Sorry, I'm looking. I edited the wrong line. Here it goes. Yeah, now it's correct. 15f is the call. Right. So we now we could also do something, but really at this point we don't care. We call our function, and there is no really a need to check for errors or something. So we only need to do those things. So move RCX. Move RDX. This is trigger. In principle, what one can do is to use to write yourself a sort of mini assembler that you kind of has, at least for the commonly used operation like move RCX, RDX, have functions which then just takes the register number and creates you the code on its own. So here we are kind of doing it manually with this online assembler, but we could make a assembler part of our code, and then you would have like a function mk layer, and then we would have, for example, for all the registers. I mean, the way this should work, if it is supposed to be simple enough, then we would have the function names encode not just the opcode name but also the addressing mode. So because we can have, for example, move rax with or generally move register with a relative address or with a constant value, and they will look slightly different. And if we really want to call functions, then we would make a function like move underscore ptr or move underscore const, and then these different functions would do different things, and like here they would, depending on the register address, intelligently select which prefix, if any, is needed for the operation. Okay, so let's go back to this. Just copy something so that we don't have to type too much, and start with that. So this is 8b 8b48 0d 0d, and then we need the address of this thingy. Where did we save that? Here. Then the next one, move RDX 48 8b is the same, just this changed to 15. And the first one was the DL handle. Oh, wait, wrong. This is not the right thing, and this is also not the right thing. The first one we said is the DLL handle, DL base offset. The second one is the ASCII string function name offset. Right, okay, just null is just null, that will not be wrong. Just 0 C0 C7 4 9. Right. And what was R9? Why do we have this twice? We don't need that twice. So RCX, RDX, R8 and R9 will be our actually for R9 we have already a code like this. Here just we need to change the one offset where we are putting it. We want the func address offset. Func address offset, and now we need to call it, and to call we already had the code here. I mean it's the exact same call, we don't actually I'm missing the comment. Now it's complete. We have the call, and here just instead of calling this address we are using this one. Load the load procedure address. Oops, not I changed it to the wrong line again. Right, and then of course we have not prepared that because we need to export here the hook message box function. So here we will comment out those things, and then let's make a new function for that. Was it one underscore? That was decal export. Install hooks void. Now since our function does not have arguments, we did not need to prepare any arguments for it, but in principle we could have now from our shellcode pass even some instructions to our function, what it is supposed to do and so on, which we could add later on even. Okay, install hooks. First let's compile this so that it's certainly built. Let's put a breakpoint here and there. Here we have our shell code. Install hook. Then let's call it install hooks. Okay. I mean we might install more than one hook, obviously. Let's roll. Continue. Okay, so we have here our step, then this part. Let's see, this will be interesting, this will be interesting, this will be interesting, and that will be interesting. Again, an annoying thing is that since we get the memory allocated in random places, each time we need to set all the breakpoints, but actually we could, after we've seen one good address to allocate to, change our code to force it to put the shellcode always at the same place. Then the breakpoints would remain valid. Here, as you see, we have a huge amount of forgotten breakpoints at random addresses. But okay, let's continue. So call. This makes our entry point. That is fine. Now the next call will be here to the load procedure function. So let's go to memory. We will see if it succeeds that it loaded an address into somewhere here at the top. And if it fails, we would also see on the registers that RAX will not be 0 but something that's a negative 32-bit integer. Okay, so here, step over. Oh, and grid crashed. Not great. Not great at all. Was our function address wrong? And I thought it would have been already done. Okay, now so we prepared this one. We should add this comment to the other call here as well. But we are not doing anything with the stack, so the stack is now perfectly aligned and it will stay aligned unless we push or pop something, which we don't. And the functions, if they do any stack manipulation, they must return the stack to the original state as by the calling convention. So we take here the base address, that's the DL handle, then we take the function name offset, that's well, the function name offset, then we set here 0, and then get the address here so that the function can return a value, and that looks all correct. Then we have a function call base address, but the offset load procedure address offset, that looks correct as well. Did we have some error with our ANSI string? Where did we constructed our string here? So function name size plus character, placeholder as 0, and function name address. That should be correct. Size, string, function name. Looks alright. Let's try it again and maybe be a bit more step by step about it. Alright, and here it looks like alignment of the comments got broken, so let's fix that quickly. Alright, so continue. Can't we make this to always show disassembly? I think there's an option for that. Show disassembly if no source available. Yeah, we don't want this stupid window here. It just adds a click, which is one click too much. Right, so this call works and this call did not. So let's call. Here's our entry point. The module was loaded, and now let's see. RCX is RCX should be the base address, or the address of the base address. Wait. Info. That's the problem. No, it's not. Wait. No, it's not. It should be right, because this is just a pivot handle. So just move the value. It's not address pivot. So move is right. It should not be allowed address. This should be correct, because the return instruction, it points to this. No, sorry, this is the value there, and this will be the address it was loaded to. 200 something as yeah, that okay, this is correct. This is definitely correct. the next is our dx. This will be our this doesn't look right. RDX should be the ASCII string. Right, is this compiled? We had an error here. For 8b, so for 8, 8b, 8b for 8, 15, and then the offset. And then the offset for func name. That looks, it looks correct, but it is not. Something here is wrong. This is definitely correct. Byte, word, double word. Okay, let's inspect the other one. R8. R8 is 0, which is correct, and R9 is an address somewhere where we are. So that was the last one was load address. Yes, that is correct. So this will be where we want the value to be saved to. But the thing is, RDX should be an address similarly to this one, and it is not. It is just garbage. So what does the code here says? That I know why I know, but that was wrong. This is wrong. RDX is wrong. This should be a load address. This must be a layer instruction. Layer RDX. Zack. Layer RDX. Okay, so for 8 is the same, but this is now 8D. 15 stays. Function name stays. Yes, that is correct. Now it's fine. Step, step. First call, second call. Continue. Now into the function here, it's fine. Okay, clear. So RCX is this where it was loaded? Yep, that's where it lives now. RDX, which is an address within the right range. R8, 0, and R9 is yeah. Now just for testing, we could go with RDX plus 8, and we say this is a char asterisk. Wait, RDX plus 8. Yeah. Char asterisk and wait. Yeah. And this gives us the right string, so this should work. So let's continue. Still crashed. But interesting. It was our call for the wrong address. Let's try again. Continue. Okay, play. Just a quick sanity check this time. Okay, this is still fine. And we call at this address, and the other called it. Oh. Why are we calling the same function? is, oh wait, am I just looking wrong? So if you recall, oh, no, it's not the same, sorry, it's not the same, it's a different position, and could be right. Let's see what's there. Null x, oops, x, y, Stern. There is 0, so we failed already here. Processor, oh my god, procedure. That explains it. Yeah, this typo is propagated everywhere, and I'm not sure that's the only one. So let's kill it. Put a breakpoint here, and then see if we actually get the address. As you see, adding some error checking would maybe not have been the worst idea. So that we check. Yeah, now we get the address here. So that if we run into such errors, we find them where it's easy to debug, and not find them where it's everything but easy to debug. Okay, so we go to here. There. Right, this is of course now completely wrong. We need to take this value now. Yes. So, right, and since we are optimistic that it will work, we this thing starts here. We open this as memory 1. So when we now step over the function, we should see here one of the pointers changing, because we should resolve the export function, and it didn't. And we got an error. Entry point not found. Why then did I not export that correctly? One step after the other. Hooked. No, so there. Is the name right? The name is an ASCII name, and it's install hooks. Oh yes, I did not export that correctly. The thing, what it does is it decorates, the compiler decorates the file names with underscores and @ and other things. To declare the function as a extern C, then it will not decorate it. Then it will work. Let's build it again. Hookdll build. Run. Where will we call this call here? Play. Quick sanity check again. Yeah. Step. Okay, RAX is 0. I did not open memory, so we don't see what I changed, but technically if R9 was this address, so if we go for this, it resolves that the address we passed to it really now contains the address of our install hooks. So we can step, and now if we really step into this, okay, we end up first in the jump table, and then we end up in our here in our function. Then we can install the hooks. We can jump out, and this already brings us to the other entry point, and everything runs as expected. Good. I guess it's a good moment in time to finish it. So I will upload the thing to the Moodle, and yeah, and if you want to use this in production, so without the debugger, you just comment out the breakpoint, because if you have the breakpoint, the application would always crash because it triggers a debugger breakpoint, but if there is no debugger connected, then it just crashes. So if we comment this out and remove this breakpoint, remove all the other breakpoints, we just see that the application is manipulated and it does not require any interaction from the debugger. Good. Yeah, and as mentioned, we could have extended this with the ability to pass one or even more arguments to our hook install hooks function, and we could have added error checking, especially also here around that if we fail to load the right address or something, that then the thing will bug out without crashing, so it would just then resume. Or we could make it differently. We could actually make it show a message box with an error like fail to load DLL or something, or both, like even ask the user whether he wants or she wants to proceed with the execution without the DLL being loaded, or whether it should crash the application. So there is a lot which could be extended on that code. But since we are almost over time, so let's finish at this. Are there any questions? Okay, if there are no questions, then we will see each other next week, and I think next week will already be the last lecture. So if there is anything you ever wanted to know about C or C++, then that would be the time to ask. So you can think during this week about some questions you may have, and we will see each other next week. Bye bye.